I gave you the term soluble the last time I had these notes. Soluble means dissolving. So if you're soluble in water, you can dissolve in water. Solubility, the ility part, just means how well can you dissolve in water? Not everything can dissolve the same way in water or to the same effect. Some things are more soluble in water than others. Boy, sugar, you can pack a lot of sugar in water. I think it's 100 milliliters of water can dissolve over 100 grams of sugar. Years ago, we used to test it out and just see how much sugar can we add, keep on stirring, and it would keep on dissolving. You never get stuff sitting at the bottom. It was ridiculous. But some things, you add a little bit, it can dissolve, but then once you reach the 5-gram mark, you can't get any more in. So that's what solubility is going over. It's still dealing with solutions. So if you remember last class, we talked about molarity with solutions. But this is going to relate to a slightly different topic or reason for why things can dissolve. Why don't you want to advance? How about that? So now you did. Now, there are different factors. My second of 3 bullet points on the slide. There are different factors that determine how well something can dissolve in water. Temperature is the one that we are going to focus on in this class. I mean, you can see on this slide, there's a graph of temperature versus grams of solute dissolved. I'll talk more about this graph today because this is one of our goals, is to learn reading this graph. Any juniors in here are going to learn all about reading graphs come early March when you take the ACT. The science section is not going to ask you to calculate molarity. They're going to give you graphs. They're going to give you data tables. So here's an example that we use in this class for a graph. Pressure. Pressure is something that deals with gases. Now, quite frankly, we are not going to talk a lot about pressure when it comes to solubility. It's a topic that I know I cover in AP Chemistry. Again, if you think about gases dissolved in water, for example, a carbonated beverage like a soda has carbon dioxide bubbles dissolved in it. But we could get those bubbles to leave faster or stay in there more likely if we varied the pressure. But again, we typically don't focus on pressure too much when it comes to solubility. Again, how quickly you can dissolve, surface area, kinetic energy, all affects that as well. Last thing on this slide. For most substances, as you increase the temperature of the water, you can dissolve more. Now, recall a couple class periods ago, we talked about how can you dissolve things faster, and heating it up would work as well. But not only does heating it up allow you to dissolve things faster, you can actually dissolve more. It's along the same principles that if the water's moving faster, it can grab hold of more stuff. So there's more water available to grab hold of things. And that's why when you look at this graph, which again I'll explain in more detail on a later slide, most things, as temperature increases on the x-axis, they slope upwards, showing that they can dissolve more at a higher temperature. However, there is an exception, that being gases. Some things actually decrease. Look at the NH3. They decrease as temperature increases. If I were to crack open my Mountain Dew and then just leave it on that desk for a while, it would lose its carbonation, its bubbles. The soda would go flat. Does that sound familiar to us? We know flat soda doesn't taste very good because it's not soda anymore. To be soda, you have to have carbon dioxide bubbles in it. However, if I were to crack it open and be like, you know what? I just don't want to have any Mountain Dew right now, but I want to save it for later because I'm not going to just pour it down the drain because that's a waste. And you don't waste Mountain Dew cold.
Right.
Exactly. I could put it in the refrigerator and keep it colder. And if I kept it colder, it would keep more of the bubbles in. Again, the mechanism behind this, I think about if things are moving fast, gases are already hard to dissolve to begin with. And if you're moving fast with your water, it's even harder to grab hold of it because dissolving involves attraction, grabbing hold of something. But if you're moving fast, it's harder to grab hold of things that are tough to grab hold of in the first place. So you want to slow it down for gases. So again, I'll explain the graph a little bit more in a future slide. That's right, that's not working. But now what we're going to go over is there are three terms to describe how potent your solution is. Now remember, molarity is a numerical value of the concentration of a solution. But at some point, you keep on adding, you keep on adding, you keep on adding. You can't dissolve anymore. And that's what a saturated solution would be. I'll give you an example. Rogers, you know what road I grew up on? Rotzenberg Road. That should tell you one of two things, Rogers. Either Rotzenbergs were loaded, so, you know, we could just name our own road after us. Or I grew up on a farm. It was not the first. It's the second. So growing up on a farm, you had to do all this different type of labor out in the fields. You had to pick rocks. Have any of you ever had to pick rocks in the field? It sucks. I mean, 8 hours a day, you're just walking. That was big enough. Throw it on the wagon. I mean, you had to bale hay back before the hay were big round bales. They were small bales, and you had to actually stand on a wagon behind it, and this baler would just be shooting it at you, and you'd have to stack it, and then you'd have to unstack it, put it on an elevator. Ooh, passed out once doing that because baling hay in 100-degree weather is not a good idea. What we would do, and it was, you know, me and about 4 or 5 others, is we'd make these big containers of Kool-Aid to take with us when we're out in the field just walking around all day. Depending upon who was making the Kool-Aid made a difference. So first off, you take those packets and you add 2 or 3 different flavors at once and you'd see what you actually were mixing together. But then you had to add sugar. Some people just kept on adding sugar when I worked on the farm. Then you shake it up to get it to dissolve. Remember, agitation. And then you drink it. Sometimes when you were done drinking it, there was still a pile of sugar at the bottom. Meaning they added so much sugar they couldn't dissolve it all. At some point, water can only hold on to so much before it can't do any more. And that's what a saturated solution is. It's the maximum amount that can be dissolved at any given temperature. If you were to try to figure out how that is, boy, if there's stuff sitting at the bottom and you shook it up really good, it's probably saturated. You can't add any more. It's just going to start sinking to the bottom. And that's how some people made our Kool-Aid. Which, boy, did that get you jacked up when you were out in the fields, but at the same time, oh, you just feel like your teeth are rotting when that's happening. Probably smarter thing for us to do when making our Kool-Aid was to make it an unsaturated solution. Just think of the prefix un. You can dissolve more. So if you're able to dissolve more, that's how my uncle actually worked on the farm then as well. That's how he usually made the Kool-Aid. He was an adult. He knew you should not dump 5 cups of sugar into a small container to make Kool-Aid. 1.5 cups is plenty, he would think. Actually, he brought along a second thing of water because usually if you drink the Kool-Aid, you have to drink some water afterwards just to wash it out because there's sugar left in your mouth. So instead of us only using molarity to describe how concentrated a solution is, we can also just use vocabulary. So unsaturated means, hey, you can still add more. You can still get it to dissolve. Far and away, ladies and gentlemen, these are the 2 most common types of solutions. Quite frankly, these words are used for things other than solutions. Have you ever heard of saturated fats? Unsaturated fats, polyunsaturated fats. That's just dealing with your carbon-hydrogen bonds. If you have the maximum number of carbon-hydrogen bonds in a fat molecule, it's a saturated fat. If there's a double bond, that means you're missing some carbon-hydrogen bonds. It's an unsaturated fat. So these terms can be used for things other than solutions. However, there's one last term I have to bring up for notes today. And this one is unusual. You will actually see this in the lab next class period. Towards the end of the hour today, I'm going to show you a little demonstration with it as well. It's called a supersaturated solution. If saturated means you've dissolved as much as you possibly can, the prefix super is saying, wait a minute, you can actually dissolve more than that. So it's a solution that holds more solute than it should be able to. Not everything can do this. The chemical that we're going to be working with at the lab benches today, it doesn't supersaturate. It's only saturated or unsaturated. However, the chemical we work with next class can do it. You just have to mess with it a little bit. Again, think about it. To dissolve more than you should be able to is unusual. I like to, with supersaturation, sometimes use the analogy of lifting up a heavy object. There's a certain amount of weight that you can lift up. But if you ever hear of these stories of times of crisis where someone was able to pick up a car on their own, they were lifting more weight than they should be able to. Kind of like Superman would do. They were supersaturated at that point. You're dissolving more than you should be able to. I even bother trying to touch it, it's not going to work. Okay. You don't have to write down anything on my last slide. This is looking at that same smaller curve that I had to start off with. This here is called a solubility curve. The x-axis shows temperature increasing. We go from 0 to 100. Once we get past 100, water's boiling. It's not great at dissolving stuff that's in the gaseous phase. The y-axis, grams of solute dissolved per 100 grams of water. Now remember, water has a density of 1, so we could call it 100 milliliters of water as well. But if I have a beaker with 100 grams, milliliters of water, how much solute, remember, thing being dissolved, can I dissolve in it? There is no mathematical equation for this. This is things that have been measured, and we're going to kind of simulate this in class today. But what you should notice is most things, as temperature increases, you can dissolve more. So what we have to do today is learn how to read it, because the lines, these lines represent saturated, the maximum amount you can dissolve at any given temperature. So if I gave you an amount that was below the line, it would be an unsaturated solution. Because if I'm underneath the maximum amount, I can still dissolve more. If for some reason I was able to dissolve more than I should be able to, I would be above the line. That would be supersaturated. So our goals today is a couple parts here. Learn about these levels of saturation, just being comfortable with the terms, but then also use a graph to be able to identify this as well. And that's where this sheet that you picked up entitled Interpreting Solubility Curves is our first practice with this. So if you can have this out, please.